In this lesson, we're going to be talking about chemical bonding. Specifically, this lesson is going to be split into 3 sections. The first one is going to be a review of the fundamental general chemistry concepts that you should know for this course, specifically how to read a periodic table and what ionic compounds are. So the first part will be a review of those 2 things. And then we're going to move on into talking in more detail about Lewis structures and their molecular shapes in lesson 1.2. And then in lesson 1.3, we're going to talk about bond and molecule polarity and how that contributes to intermolecular forces. All right, so let's start with the first part of this lesson, which is a review of general chemistry. So these are going to be our learning objectives, and we are going to walk through each one throughout this lesson. Okay, so let's talk about our first learning objective, which is going to be describing the basic features of the periodic table. So here are a few terms that you should know. I will be using many of these terms in class, and so I am expecting you to know what I mean when I use these terms. All right, so let's look at group. What do we mean when we talk about a group in a periodic table? So you will notice that the group number exists up here. That is going to be your columns. So all of these are group numbers. Okay. You're also going to see that there are 2 annotations here. We can have this one that has a number and a letter, and then the other numbering, which is just numbers. Okay. So we will be using both interchangeably, but in any case, we can count the columns, or you should know what I mean when I say group number 1, I am talking about the first column. If I say group number 2, I'm talking about the second, and so on. Okay, then we have period. Period is going to be your rows. So this is period 1, that's row 1, this will be period 2, and so on. So if I'm talking about potassium, which is this one here, I'm talking about the element that is in period 4 and group 1. Main group elements are going to be the ones that are shaded in blue. These are your main group elements. Okay, we will be focused in this course only on main group elements, but you should know that we also have transition elements. Right? We do have these transition elements in orange and those that are called inner transition elements. Again, we won't be dealing with those in this course, but you should know what I mean when I say transition elements. Okay, and then we have these other terms that I will be expecting you to know. We are going, in the next slide, I'm going to talk in more detail about metals, nonmetals, and metalloids, just being able to determine which ones those are by just looking at the periodic table. But you should also know alkali metals are those that are in group 1. And if I say alkaline earth metals, I'm talking about the metals that are in group 2. So this entire column, beryllium, magnesium, calcium, and so on, all of those are alkaline earth metals. Halogens are going to be elements in this group. Okay, so all of the elements in that column are going to be referred to as halogens. And finally, noble gases, those are going to be all of the elements in the very last column of our periodic table. Okay? So these are all terms that you should know. All right, so what do we mean by metal, metalloid, and a nonmetal? Well, all of your metals are highlighted or are shaded in green here, and your nonmetals are going to be in blue. Okay, so as you can see, the periodic table is mostly metals, but we will be talking about in this course about the main group metals, which are going to be these here. And we're going to be talking about, and also these metals here. Okay, and then we're going to be talking about nonmetals, which are the blue ones in the upper right-hand corner of your table. And the reason this distinction is important is because when we talk about ionic compounds, let's recall that ionic compounds means that we have a metal binding or bonding to a nonmetal. Okay, so what would this look like? Well, for example, I can take potassium, which is a metal, and if it bonds to bromine, for example, which is a nonmetal, I would have KBr. Okay? And I can look at KBr, this formula, and know this is an ionic compound because I can identify that potassium is a metal and that bromine is a nonmetal. We're also going to talk about covalent compounds. You should know how to identify a covalent compound from its chemical formula. This is going to be a nonmetal bonded to another nonmetal. So a common example of this is just H2O, water. Why is this a covalent compound? Well, oxygen is here, it's a nonmetal. Hydrogen is here, it's also a nonmetal. Okay, so what this means is you have 2 nonmetals binding together, that is going to be a covalent compound. All right. Now let's look at a tile. Let's zoom into one of the tiles in the periodic table. What should you know from here? First thing to note is the atomic number in each one of those tiles. So recall that your atomic number is the same thing as or it tells you the number of protons in that element. So in this example here, the periodic table is telling you that lithium, the element lithium, has an atomic number of 3, which means it has 3 protons. So what this also means is that the number of protons is going to tell you the identity of the element. That means that if you have an atomic number of 3, you can only be lithium. Okay? If you have an atomic number of 4, you can only be beryllium. Right? So that's going to tell you which element you are dealing with. Protons have a positive charge. Electrons, which I will often abbreviate this word with this symbol. That means electrons. Electrons have a negative charge. So let's think about lithium, negative charge. Lithium in this example, lithium has 3 protons because its atomic number is 3. So that means that these protons, since they are positively charged, they are contributing a +3 charge. Okay. If my atom is, or my element is neutral, that means it must also have 3 electrons. Why is that? Well, each electron is going to contribute a negative charge. I have 3 of them, so that's -3. If you add the positive 3 charges with the -3 charges, that gives you a total of 0. +3 - 3 is 0. This is what we mean by a neutral atom. Neutral atom. So if you have a neutral atom, the number of electrons is going to equal your atomic number, meaning your number of protons, in order for it to cancel out. So for a neutral element, the atomic number equals the total number of electrons. So why am I specifying this total? Well, we have the concept of total electrons, and then we have the concept of valence electrons. And the reason we make this distinction is because it's the valence electrons that are going to be responsible or involved in chemical bonding. Okay? So valence electrons, the definition of valence electrons is that these are the electrons that are in the outer shell. Okay, so these are the ones that are going to participate in bonding. So let's look at lithium again as an example. So here I'm going to write the number of valence electrons, and then to compare with the total number of electrons. So we can understand this concept that valence electrons doesn't always equal the total number of electrons, all right? So let's just start with lithium, which was our example in the previous slide. Lithium had 1 valence electron. And well, it had a total of 3 electrons. And of those 3 electrons, 1 of them is a valence electron. Okay? And I'm going to describe in a minute how to identify that it has one valence electron. But the point here is that while lithium had a total of 3 electrons, because again, lithium has an atomic number of 3, so that means it must have 3 electrons to cancel out the positive charge. Of those 3 electrons, only 1 is going to be valence. So only 1 will participate in bonding. So how do I know that? How can I determine the number of valence electrons? So this is going to be our third learning objective, which is how to determine the number of valence electrons by just looking at the periodic table. And this is a skill you will need throughout the course. So for main group elements, the main group number is going to indicate the number of valence electrons. So what does that mean? Well, our main group elements are going to be those that are not transition elements. So we're not going to consider these. So that means this is going to be group number 1, group number 2. We skip the transitions, 3, 4, 5, 6, 7, and 8. So those are the main group column numbers, right? That is going to be equal to the number of valence electrons. So you see lithium is in the first group, which is why it has 1 valence electron. Let's look at a few other examples. We have carbon. Let's first think about the total number of electrons in carbon. So if we locate carbon, we see carbon has 6 as an atomic number. That means it has 6 protons, which are positively charged. That means it must have 6 electrons, which are negatively charged to cancel out to 0 because it's neutral. So this means that if it has 6 protons, it must have 6 electrons. Now, how many of those electrons are valence electrons? Well, now we need to turn to the main group number. And we see that the main group number or column number for carbon is 4. So carbon has 4 valence electrons. Let's look at another example. Let's look at calcium. Calcium is going to be over here. Its atomic number is 20. So it has a total of 20 electrons because it's neutral. It doesn't have a charge. Okay. And then calcium is going to have 2 valence electrons because it is in the second group, right? So it has 2 valence. What about bromine? Well, bromine is over here. Here's our bromine. Atomic number of 35 means it has 35 electrons as well if it's a neutral atom. And then the number of valence electrons is going to be 7 because it's in the 7th group, in the main group elements. All right. Lastly, we have neon. Neon is over here. It has an atomic number of 10, so it has 10 total electrons. And the number of valence electrons is going to be 1, 2, 3, 4, 5, 6, 7, 8. It's in that last column, so it has 8 valence electrons. All right, so now that we know how to extract the number of valence electrons, which again, it is just the column number of only the main group elements, that is going to be equal to the number of valence electrons for that element. Now that we know how to do that, we can express that, we can communicate the number of valence electrons using electron-dot symbols. All right, so how do these work? So recall that when you're drawing an electron-dot symbol, you're going to use a dot to represent every valence electron. So we're not talking about total electrons here. Again, now we're focusing in on valence electrons because those are the ones that participate in chemical bonding. All right, so I am going to just keep track of my valence electrons here in this table. Okay, so let's do the first example, hydrogen. How would we draw the electron dot symbol for hydrogen? Well, you first locate its electron symbol, or its a chemical symbol, and that's going to be an H for hydrogen. And then we see that hydrogen is in the first column of the main group elements, so it's going to have just 1 valence electron, and therefore it receives 1 dot. Okay. So each dot represents 1 valence electron. The dots are then placed on the 4 sides of an element symbol. So let's look at carbon as an example. Carbon is here. We identify that it has 1, 2, 3, 4 valence electrons. So it has a total of 4 dots around it. And you'll notice that the dots are put 1 in each of the 4 sides first before you begin to pair them. So what does it mean to pair electrons? Well, let's look at oxygen as an example. Oxygen is here. It has 6 valence electrons because this is 4, 5, 6 valence. So that means that oxygen is going to have 6 dots around it. So how we would do this, the convention is to start first putting single dots on each of the 4 sides, and then you can start pairing them. So I have put 4 valence electrons so far. I need 6, so 5 and 6. So you can draw it, or you can draw the dot structure like this, or you can draw it as how it has been drawn here, where the lone pair is down here at the bottom. Either of these are correct. You can draw either one. This is correct. And then lastly, we have chlorine, which is in this column here, column 7. So that means it must have 7 valence electrons. And then you see it has 7 dots around it. Okay, so these are electron dot symbols. All right, so now let's look at what kind of elements we're going to encounter mostly in this course. So the types of elements we're going to be looking at are mostly this here. Why is that? Are going to be these, okay? So carbon, oxygen, and hydrogen, these elements are going to be present in your lipids, which means your fats, and it's going to be present in carbs, or carbohydrates, which are your sugars. Then all of those plus the nitrogen are going to be present in proteins. Okay. And so that's why this is going to be, these 4 are 96% of the mass of the human body. So if we look at our periodic table, in this course, we're mostly going to be dealing with these elements and hydrogen. Now, we of course are going to be talking about other elements because there are major minerals that are like potassium, chlorine, and so on. We have some trace elements as well, which are some other metals included. But the majority of what we will be talking about is going to be these 4 elements. Okay, so let's just do a little bit of practice so that we can reinforce what we just recalled. Okay. So let's start with A. Here, it is asking to give the electron dot symbol of each of the elements. So first, let's locate bromine. Bromine is going to be here. It's Br. It's this element. Okay. So that means it has 1, 2, 3, 4, 5, 6, 7 valence electrons. So I draw the chemical symbol first, or the element symbol, and then I do 1, 2, 3, 4, and now I can start pairing them. 5, 6, 7. Okay. All right, let's do lithium, which we've already talked about. Lithium has a Li symbol, and it's located here on the table, and it has it has 1 valence electron because it is sitting in the first group. So we just draw it like this. Let's look at aluminum. Aluminum is located here. And this one is going to have 3 valence electrons because it's in that third column of the main group elements. So Al will have 1, 2, and 3. Let's find sulfur. Sulfur is going to be this one here. So I write S, and then I identify that it has 6 valence electrons. So it will get 6 dots. Lastly, we have neon. Neon is here. It is a noble gas, and it has 8 valence electrons. All noble gases, because they're all in this column, in the last column, they will all have 8 valence electrons. All right, so now that we have recalled valence electrons and we understand how to extract them from the periodic table, and we know how to draw our dot structures, we are ready to recall how chemical bonding works. Right? Specifically, we're going to talk about ionic bonding, and next time we're going to talk about covalent bonding. So let's just briefly review what these two things are. So first, what is bonding? Bonding is the joining of 2 atoms via their valence electrons. Okay, so again, that's what we're concerned with. And this is to achieve a stable arrangement. What do we mean by a stable arrangement? That is going to be the octet rule. So what elements will do is they can gain, they can lose, or they can share their valence electrons. Okay? And they're going to do this in order to achieve the electron configuration of the noble gas closest to them. And this is how we define the octet rule. We're going to talk a little bit more about that on the next slide. So first, let's recall what the 2 types of bonding are. We have ionic bonding and we have covalent bonding. So ionic bonding is going to be the result from the transfer of electrons. When you transfer electrons, you gain them or lose them because they're being transferred. You're not sharing them. And because of this, because you're going to be either gaining an electron or losing electrons, that is how we're going to generate charges. And this is why we use the term ions to describe whether it's a positively charged ion or a negatively charged species. And we'll review that in just a minute. For covalent bonding, that is the result of sharing electrons. So because you're not giving up an electron which has a negative charge or gaining an electron which has a negative charge, in covalent bonding, we are just sharing the electrons. That means no charges are generated. Okay. So the sharing of electrons is not going to generate a charge. All right, so let's recall what an ionic compound is. So an ionic bond is formed when a metal transfers 1 or more electrons to a nonmetal. So it has to be an element that is on the left-hand side of your table. So these that are shaded in green are going to be your metals, and the nonmetals again are your blue. Right? So when your nonmetals. So when one of the metals binds with a nonmetal, then you get an ionic compound. Why do you get an ionic compound? So let's look here at the example. The first thing I want to describe or define is what we mean by the noble gas closest to something. What do we mean by that octet? So what this means is that if you have the number of electrons of a noble gas, so if I have, for example, 10 total electrons, then that means that I have the electron configuration of neon because I have 10 electrons. And then that also means that I have 8 valence electrons. Because again, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons if you are neon. Okay? So if you have 18 electrons, you're argon, that means you also have 8 valence electrons. So if the total of electrons that you have is 18, that means you have the argon configuration. So it also means that you have 8 valence electrons. So that's what we mean by electron configuration of a noble gas. All right. So now let's talk about what we mean by a transfer. All right. So a transfer happens in order to achieve that electron configuration of the noble gas. All right, so when we transfer something, if we look at this example here, we have one element that has one valence electron. We have another element that has 7 valence electrons. Okay? And then what they're showing here is that an electron is being transferred. So the first element, element M, is giving up its electron to element X. So let's put an example here. Let's talk about sodium, which is a metal. So I'm going to put sodium. Sodium has 1 valence electron. So let's imagine M is sodium. And let's imagine X is chlorine, which is here. And chlorine, because it's in the 7th group, is going to have 7 valence electrons. So if you have sodium and chlorine trying to form a bond, sodium is going to transfer the electron to chlorine, okay, which is what is being shown here. And when it does that, sodium is giving up its electron, which has a negative charge. So that means it now has an excess of 1 positive charge, because it has lost that 1 negative. And chlorine, however, has gained a negative charge because it has gained an electron. So that means that chlorine now has 1 more electron. So I include that in its dot symbol. It has 8, and it now has gained an electron. So that gives it an excess of a negative charge. Right? So this is why a transfer generates an ionic charge, is because you are losing or gaining an electron. Right? Recall that when you gain a positive charge, or when you have a positive charge, that is a cation. And we refer to this species as an anion. So when you gain an electron, you now have a negative charge. We call that an anion. All right. So that is what we mean by a transfer. And when you transfer an electron, you can generate a cation and an anion. So now, how do I know that sodium is only going to give up 1 electron? So why does chlorine gain and why does sodium lose? So this is where we look at our periodic table, and then we need to determine we need to determine the closest noble gas to each of the species we're concerned with. So let's look at chlorine. Okay. How do I know that chlorine is going to gain electrons rather than lose them? So the first thing that we're going to see is that chlorine has valence electrons. It has a total of 7 valence electrons. Okay, so it's here. Now, chlorine has the noble gases argon and neon closest to it. So if chlorine were to gain an electron, it now has 18 electrons, which means it has the configuration of argon, which means that it has 8 valence electrons. So if chlorine gains 1, it has 8 valence electrons. If chlorine loses 7, it can lose 1, 2, 3, 4, skip the transitions, 5, 6, 7. It now has the electron configuration of neon. And neon also has 8 valence electrons. But now, why would chlorine want to gain 1? Well, gaining 1 electron is easier than losing 7 electrons. So that means that chlorine will tend to gain an electron to achieve that octet rule, which just means 8 valence electrons around it. So chlorine is going to want to gain electrons to achieve 8. So 7, it's going to specifically gain 1 electron. Gain 1 electron. What about sodium? Well, sodium is over here. It can either gain 7 electrons, right? So 1, 2, 3, 4, 5, 6, 7 to achieve the argon configuration, or it can lose 1 electron. If it loses 1, it now has the neon configuration. So of course, sodium is going to prefer to just lose 1 instead of trying to gain 7 from somewhere else. Okay, it's going to be easier for sodium to lose 1 to gain its octet. So here, normally sodium has 1 valence electron, and it's going to lose that electron. It's going to lose 1 electron. It loses 1 electron in order to gain the configuration closest to itself. Okay, so this is how you can determine the charge that you are going to generate for a particular atom. So let's put that into practice. This is just to reiterate that cations are going to be the positively charged species, and the anions are going to be your negatively charged species. So let's go ahead and see how we can use the periodic table to determine the charge of an ion. Again, this should be review. All right, so let's look at this problem. So we're going to use the group number to determine the charge on an ion derived from each element. So the group number is what's going to tell us how many valence electrons it has. And then that's how we can determine how many need to be transferred, meaning how many need to be gained or lost in order to achieve that noble gas configuration. So here I'm going to write the neutral species, then I'm going to write the ion that we're going to generate, and then the type of ion, whether it's a cation or an anion. All right, let's start with magnesium. Let's first locate magnesium on the table. It's this one here. So it has 1 and 2 valence electrons. So magnesium, this is what the neutral species looks like. Right? So magnesium can either gain 6 electrons, 1, 2, 3, 4, 5, 6, to achieve the argon configuration, which is 8 valence electrons total, or it can lose those 2 to achieve the neon configuration. Magnesium is going to prefer to lose 2 rather than gain 7, because neon is closer to magnesium than argon. Right? So it's going to lose 2 electrons. So what that means is that it has lost 2 negative charges. So now it has an excess of 2 positive charges because it has lost those 2 negatives, right? So that means that we have formed a cation. Let's look at iodine. Iodine is here on your table. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. So that means I need to write 7 dots. And now iodine is going to prefer to gain 1 electron to become like xenon rather than lose 7 to become like krypton. So that means that it gains 1 electron. That's the shortest path. And so that means I have to add a dot to its structure, to its electron dot symbol. And then it gains 1 electron. So that means it has gained 1 negative charge. So it becomes negatively charged. And therefore we have generated an ion. All right, let's talk selenium. Se is right here. So that means it's going to have 6 valence electrons. So 1, 2, 3, 4, 5, 6. Selenium would rather pick up 2 electrons rather than give up 6. So it's going to pick up 2 electrons. So 1 here and 1 there. And then that means that if I have picked up 2 electrons, I have picked up 2 negative charges. And therefore, selenium is going to have a 2 minus charge. And that makes it, sorry, this is anion. That also makes it an anion. Right. Let's do this last problem here. This is rubidium. Where is rubidium? It is right here. It's in that first group. So that means it has 1 valence electron. Well, it's going to prefer to lose 1 rather than gain 7. So in order to reach 8 electrons in its outer shell, so rubidium is going to lose that 1 valence electron, and because it lost 1 negative charge, it now has an excess of a positive charge. And this is also going to be a cation. Right. Okay, so now that we remember how to determine, you should be able to look at a table and know whether something is going to gain electrons or lose them, and how many of each it's going to gain, what kind of charge you will generate. So now that we know how to generate charges, let's recall how to put ions together in what we call an ionic compound. So the main thing to remember here is that the sum of the charges of your ionic compound, so your cation and your anion, the sum of those two must equal 0 overall, because ionic compounds are neutral compounds. So here I'm going to draw our ions. We're going to have to look at the table and determine what kind of ions we would generate. And then here we're going to put the formula of the compound. All right, so we have sodium. Sodium is here. Sodium is going to have 1 valence electron. Then in order to achieve the octet rule, or to achieve the configuration of the noble gas closest to sodium, sodium is going to lose 1 electron to become like neon, rather than gain 7 electrons to become like argon. So it's going to lose 1 electron. That means sodium is going to have a positive charge. The other ion is going to be bromine. We see bromine is all the way here at the very end. It is a halogen. All halogens have 7 valence electrons. So that means this is the ion that we have. And because it gained that electron, right, bromine is going to want to gain an electron rather than lose all 7. Bromine is going to gain that electron to become like krypton, and then that gives it that negative charge. So that means that when sodium and bromine bond together, you are going to need 1 of each, because sodium ion is going to have a positive charge, the bromine ion will have a negative charge, and therefore a positive and a negative equal 0. Let's look at the next one. We have barium. Barium is here, and then we have oxygen, which is here. All right, barium is in the second group, so it's going to have 2 valence electrons. Now barium can lose 2 electrons. It can lose 1, 2 to become like this noble gas, or it can gain 6 to become like this noble gas. Of course, it's going to prefer to lose 2. So if it loses 2 electrons, that means it now has an excess of 2 positive charges. So barium has a 2+ charge. Now let's look at oxygen. Oxygen is going to want to gain 2. That's the shortest path to become like neon. So oxygen will have 8 valence electrons around it, and then it will have a 2- charge. Now, when these two bond together, barium has a 2+, oxygen has a 2-. Those two will cancel out to 0. So you only need one of each element, each ion. Right, now we have magnesium and we have iodine. Magnesium has 2 valence electrons. It's going to want to give up those 2 valence electrons. So now it has a 2+ charge. Iodine has 7 valence electrons. So it's going to want to pick up an extra electron to make 8. And so that gives it a negative charge. So that means that magnesium has a 2+ charge. You're going to need 2 iodines to cancel out that 2+ charge, because each iodine contributes just 1 negative. So you're going to need 2 to make a total of 2 negative. So that 2+ and 2- equals 0. Lastly, let's look at lithium and oxygen. Lithium has 1 valence electron, and it's going to want to donate that 1 rather than gain 7. So that means it gains a positive charge. Oxygen, we already said, it's going to pick up 2 electrons to make 8 in its outer shell. So now it has a 2-. Well, this means that to cancel out the 2- from the oxygen ion, we're going to need 2 lithiums, each with 1 positive charge. Okay? And that's going to be its chemical formula. All right. So this is here is just for your reference. This is just to remind you that metals will tend to lose electrons, meaning they're going to gain a positive charge. So they're going to have positive charge. And our nonmetals are going to tend to gain an electron. And because they gain that electron, they will have negative charges. So again, this is just for your reference, for you to recall how to generate these, but you should be able to just look at a regular periodic table and determine what kind of ions you would generate. This is a review on how to write, again, your ionic compound formulas. We did an example just now, but this is, again, just to help you refresh on how to write those compound formulas. Okay. We do have ions in the bodies that have a functional role. So these are like calcium 2+. That's going to be an ion that we find in bones. Sodium and potassium, these ions are found in our bodily fluids, and so on. Iron 2+ is present in our blood. So these ions do have functional roles in our bodies. Right. Also, you will need to review how to name ionic compounds. I will sometimes use names of ionic compounds, and I do expect that you will know what I'm referring to when I use these names. Right. And so we will be looking at this in more depth in Lab 1, just as a review. And I have also provided the table here of the polyatomic ions, specifically polyatomic anions, for your reference. All right, so next up, we're going to talk about covalent bonds. So let's just briefly compare how this is different from an ionic bond, which is everything we've been talking about so far. So again, your ionic bond is made when an electron is transferred. Covalent bonds are formed when electrons are shared. Specifically, the sharing is going to happen between 2 nonmetals. So here's an example of that, just what it would look like. Let's say you have atom X and another atom X. Let's just say it's chlorine. Okay, chlorine has 7 valence electrons, and then there's another chlorine that has 7 valence electrons. And then here, instead of one giving an electron to the other completely to generate ions, here we're actually going to share the electrons. So these electrons here in red are actually being shared. What this means is that those 2 electrons belong to the element on the left-hand side, and they also belong to the elements on the right-hand side. So that means that if this was chlorine, you would get a bond like this, where 2 chlorines are bonded together, and the electrons that are involved in that bond are being shared by both chlorines. Okay? Here's an example of what that would look like. Here we have hydrogen and fluorine. If they were to form a covalent bond, how that would work is hydrogen with its 1 valence electron would share its electron with the fluorine. Okay. You'll notice that fluorine has one electron that is unpaired, which is this one here. So they will go ahead and form a pair in order to make a bond. And this specifically, because those are being shared, it's called a covalent bond. So these two electrons belong to hydrogen, but they also belong to fluorine, right? And we will talk in much more detail about these next. So that will complete our review of the general chemistry concepts that you should know in order to be successful in this course. This next lesson is going to focus on covalent compounds, which is what we are going to be focusing on for the rest of the semester. So we will go into more detail about these three learning objectives.